in an experiment.
And we don't know yet.
Why is light so far?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This week, how to turn a plastic into a lubricant.
And how a yeast can help make a cancer drug. I'm Marian Hunsberger.
And I'm Nick Petrichow. This week in Nature, researchers have shown that a common plastic can be turned into a lubricant, rather than heading to landfill. The plastic in question is polyvinyl chloride, better known as PVC. The poly may give you a clue to its structure, if you remember your high school chemistry. It's made up of hydrocarbons, carbon and hydrogen atoms with a chlorine atom on the side, repeated many times in a long chain. This relatively simple structure belies how versatile it is, coming in harder and more flexible forms. That means it's everywhere. It's in pipes, doors, bottles, packaging, and probably in your pocket, as it's often the plastic of choice to make credit cards. But while it's useful for making a lot of products, there is the question of what to do with it at the end of its life. It can be recycled, but the process is difficult, and in many cases, the resulting recycled products aren't worth much more than the original PVC, meaning that a lot of it just ends up in landfill. This new work, though, may show a way to make a much more valuable product out of PVC, and therefore give an economic incentive to recycle it. That product? Lubricant. And by lubricant, I mean the kind you put in your car. This lubricant, often made from a chemical called polyalpha olefin, can fetch a price of $3,200 to $6,000 per metric ton. Much higher than the perhaps $1,000 per metric ton that PVC is worth. I called up Greg Liu, one of the authors behind this transformative work, to learn more about his lubricant making process, and he told me how he and his team got started in tackling PVC.
So initially we thought about, okay, can we use them to make materials? But after a few years of try and error, and we realized that actually it's very difficult to make those materials, especially to reuse them in the plastic field. Then we realized, okay, maybe we don't have to close the plastic loop to just use it as a new plastic, but we can turn it into something else.
And so tell us, what is that idea? What did you want to do to not turn them into plastic, but to turn them into what else?
At first, we were thinking about if it's polyvinyl chloride, if we can take all the hydrocarbon background, so maybe we can use it as a backbone for linkage. And if we can attach something else to that, then we may be able to make a cross-linked PE version of material. The motivation there is actually very simple, right? Because PVC is widely used in pipes. And nowadays, especially in Europe and in the United States, and there are more pipes made of cross-linked PE or XPE. So if we can take the old PVC pipes and make it into XPE, that means we can still use them in piping and similar applications. So we tried a lot of times to make them into cross-linking materials, and we made some materials. It's some materials that potentially can be usable, but it's not the performance that we would like to be. And then we realized, okay, what if we break it down further, and what else we can do about it? And that's why we came up with the lubricant idea.
But the question, I suppose, is how does one turn PVC into said lubricant? So how did you actually go about doing it?
So when we got the first experiment results from the attempt to make it XPE, we made some material that is like soft, very gooey, kind of tacky, and we don't know what to do with it. And if you let the reaction to go further, it's a little bit viscous. And then we realized, oh, it's a viscous honey like material. So maybe that's not the best material for XPE, but it's a nice material for lubricant, and that's how we actually stumbled upon it.
Bit of serendipity there then, but I suppose that having this sort of gooey substance isn't quite a lubricant, so did you have to do more to actually get it to be a proper lubricant?
Yes, so we have to do some more chemistry to make it happen. And then it becomes a question, maybe a little bit more technical here now, is that we need to controllably break the chains in a way that we can attach some new molecules onto it, and then we can make the molecule in a range that is suitable for lubricants. And that's how we perform the systematic study. How do we tune the reaction conditions like temperature, time? All those are the downstream optimization process to make the high quality lubricant.
So what's the magic formula then? How would I take my PVC and turn it into a lubricant?
So at the end, we kind of borrowed the information from the traditional classical lubricant manufacturing industry. And typically, high quality lubricants such as polyalpha olefin is made of alpha olefin. And PVC provides the backbone structure for polyalpha olefin. Then we want to still bring the branch structures from the alpha olefin to produce that similar molecular structure. And then what we did is that we can actually bring the alpha olefins into the reaction in a controlled manner, and then we can attach these alpha olefins to the backbone of a PVC. Then we produce a molecule that mimics the classical polyalpha olefin and have a similar properties.
So it's about, I guess, sort of breaking up the PVC and attaching different molecules to it to make it this sort of lubricant. Is that about right?
Yes, you can think about an analogy is that you have a template that is made by PVC, and then there's many slots that you can insert some bricks onto it. So the alpha olefin are like the smaller bricks that can be inserted into the template. And then you can basically just edit in the original PVC template using the new blocks of alpha olefins to make the polyalpha olefin structure.
And when you did this and you made this lubricant, is it as good as the sort of lubricants I can buy off the shelf? Is it similar?
After optimization and further experiments, we made a polyalpha olefin that has a very similar properties to the existing commercial products out there. They're comparable, have very similar viscosity indexes and other performances. So now I think it can be potentially used as a lubricant for future applications.
As you mentioned, PVC has a lot of different uses and it's got different additives and different things added to it to give it different properties. Were you able to do this for a broad range of different PVCs?
Actually, we test a broader range of end products from PVC. In the paper, we report a few examples, including credit cards, toy frogs, PVC pipes, and gloves that is made of PVC. Right. So the different products out there that range from like household use to even for children use. I have a little child at home, so we use some of those products there and to make this research.
They were his toys.
Yeah.
Okay, great. And so obviously then it sounds like it works for a broad range of different PVCs, but you wanted to make something that would be sort of economically viable and companies could do this, or, you know, industry could do this. How easily would this process that you've shown here be to scale up?
We perform some smaller scale up, not an industrial scale up in our laboratory. Of course, we don't have that capability yet, but we're developing those capabilities. We are able to scale up our small reactions in our laboratory. So we show very early stage scalability already in our laboratory, and this is feasible. And I think with some more engineering, or maybe chemical engineering or materials engineering out there, I think this should be feasible in the future.
And so what would you say then are the next steps if someone were to try and do this on a larger scale?
So right now, we use the PVC as a source of the waste feedstock. And we also use alpha olefins from the conventional petroleum industry. Our next goal, and as we are actually working on right now, is we want to push this into a fully plastic waste derived product. Hopefully, we will be able to replace the alpha olefins with renewable or maybe sustainable alpha olefins as well.
And so is that your hope for the future, to try and resolve much of the plastic waste problem?
My vision here is that we want to rethink about the chemical industry and rethink about how we manufacture chemicals and materials in the past. Almost everything around us has some chemical and materials component, and it's from the chemical industry or materials industry. And if we can rethink about how we manufacture our products in the future, we may be able to build a more sustainable chemical manufacturing pipeline down the road.
That was Greg Liu from Virginia Tech in the US. For a smooth ride over to more on lubricants, you can check out the show notes for some links.
I see what you did there. Next up, it's the research highlights with Katrina Clark.
Baker's yeast could spare an endangered plant, as researchers have found a way to engineer the fungus to make a cancer drug. Millions of people take the drugs etoposide and tanipicide, which are used to treat cancers of the lung, blood, and other organs. But making them is tough and relies on compounds from endangered plants. So, researchers engineered Baker's yeast to produce some of the necessary molecules. By introducing 60 genetic edits and 45 new genes into the yeast, the team were able to produce the building blocks for the drugs in 3 days of fermentation. These compounds could then be turned into the etoposide and tanipicide in a single chemical step. The researchers hope that this work shows the potential of such approaches to produce drugs, especially because this process had substantially higher yields than the conventional plant-based approach. Transform your understanding of that research over at Science. Sickle-cell disease can lead to prematurely old cells, but researchers may be able to reverse it with existing drugs. People with sickle-cell disease have misshapen red blood cells that don't function properly. While the trait offers some protection against malaria, there are a range of complications. To understand how the disease affects blood-forming cells, a team of researchers studied stem cells from the bone marrow of mice that had a version of sickle-cell disease. They found that these stem cells that give rise to the rest of blood cells had signs of premature senescence, a process where the cells stop multiplying but are not destroyed. But the team also found a possible way to reverse this. By giving the cancer drug navitoclax to the mice, they were able to restore stem cell function to cells comparable to mice without sickle cell disease. Other drugs known to battle senescence also showed promise in the mice. The researchers hope that such treatments could bolster existing therapies for sickle cell. You can read more about that research over at Science Translational Medicine.
And that's all for this week. If you'd like to stay in touch with us, you can. We're at Nature Podcast on social media, or you can drop us an email to podcast@nature.com. I'm Maren Hunsberger.
And I'm Nick Petrochow. Thanks for listening.
Bye.